differenti decisamente.
That's why I have one end less in this way. But I will try. Today I would like to so after yesterday's introduction, we pass now to see more detailed something about our aerospace propulsion. And in particular today, what I would like to do is to introduce and recall the medium we use for propulsion. I would like also to make a classification of the different kinds of propulsion devices that we're going to use or to consider. And then also at the end, I would like to underline some specific aspects of rocket propulsion devices towards thrust generation. So as first step, let's start talking about the medium. The medium we are going to use. When we talk about marine propulsion or ground propulsion, it's rather obvious that we use ground, or better, water and ground. This is rather obvious. If we are in the atmosphere, we enter the field of aerospace propulsion, and of course, we would like to use the medium we have available, that means the atmosphere. And so there are, in particular, similarities between the aerospace propulsion and the marine propulsion, because we have a fluid as a medium in both cases. So the first thing we imagine is use similar things. So if we use propellers for marine propulsion, we can use also propellers for within the atmosphere. In this kind of media that I'm talking about, what we do is that we try to provide energy towards this medium. We accelerate the medium. Imagine a propeller, we accelerate the atmospheric air. Similarly, the water in marine propulsion. So, of course, we accelerate the medium, and to do that, we exert a force on it, and as a reaction, we have a force on our vehicle. In the atmosphere, of course, I'm mentioning atmospheric flight, and in aerospace propulsion, just today and tomorrow, we will also make some reference to what we call air-breathing engines, or let's say propulsion within the atmosphere. Why I mention this? Because even if today launchers are based only on rocket propulsion, there is always the idea to exploit as much as possible the available medium, which is the atmosphere. So in the first part of the flight of a launcher, at least if you are talking about launchers, but let's say there is also something about satellites we will mention shortly, we would like to exploit the available medium that can be the atmosphere in this case. So it's correct to at least mention it as possible, to keep this in mind as a possible way to exploit other means of propulsion. So we have in the atmosphere, if we think of a propeller, what we can consider that we provide some mechanical force. We have an engine that can be an internal combustion engine, that can be an electric engine or motor. It can be also a turbine engine, provide the power to a shaft, and this shaft transfers the energy to a propeller that in turn accelerate the air. Another way of exploiting the atmosphere is to directly accelerate the available medium, the atmosphere. Let's say exploiting thermodynamics. And we have in this case what we call a jet. In this case, the working fluid is the same as the accelerated medium. This is a peculiar case because typically in the other engines I listed, and also in ground propulsion, we don't use the same medium to get the power and as the accelerated medium, let's say. Well, if the medium is mainly the atmosphere, we call it, as you know, we call this kind of propulsion devices as air-breathing engines. So they take they exploit the medium, which is atmosphere. What we do in space. In deep space, we have practically no medium. So what we do is that we bring our medium with ourselves. We don't have external medium. We provide ourselves with a medium. In this way, we don't exploit, because unavailable, the possible air, the atmosphere. So we don't breathe air. And in this case, we have what we call rockets, rocket engines, rocket motors, thrusters, all based on the principles of rocket propulsion. So if we can try to summarize, we have a propeller here that provides accelerated A, and we have that some air is coming in this direction, and this is the propeller-based devices. There's something missing here, of course. If we have here an engine that provides the needed amount of energy to the propeller, and of course we need some power source, because nothing is for free. If we consider an air-breathing engine, we have one step less, because engine and propeller are the same thing. I mean, or better, the engine and the device accelerating the atmospheric air is only a single part. So we have here our engine, accelerated air plus fuel, and of course power. don't forget you always need power. And if so this is the principle of propeller engines. These are air-breathing engines, jet engines. And then we have rocket engines where let's call it engine here, and you have accelerated gas. The exhaust gas. So perhaps in this way you still hear me. I changed the position of the microphone. I hope that it can be heard. So to accelerate, in any case, to accelerate our medium, either it's internal medium or external medium, what we have to do is to spend some power. We have to make work. We have to exert a force from a moving device or a moving medium, so we have to make a work which is a cost. And at the end, this tells us that, so here of course we need power. So at the end, thrust is the result of more or less complicated transformation of energy from a primary energy that we have somewhere that we transform in different ways up to get thrust. So this helps us to make a general classification. Let's consider not spectrum in this way, the other way. So let's consider aerospace propulsion in general. And we can identify different families based on which is the medium. So it can be the atmosphere, medium is on board, or other medium. First three kinds of subdivision of aerospace propulsion devices. So if medium is the atmosphere, here we can identify again three options. These are those that, imagine at this point, we have engines based on propellers. Then we have engines based on jet propulsion. So let's call it jet. And these are the air-breathing engines. And I left another option, which is, for instance, just to mention that there is also something more exotic, that is, for instance, ram electric propulsion. About in case the medium is on board, we can consider again, let's say something similar based on jets, and let's say these are what we will refer to as thermal rockets. Or, for the moment, we say other. So that we can identify here our jet propulsion, either air breathing or rocket, and we have here something which is not jet propulsion. Jet propulsion is based on the thermodynamic acceleration of a medium. And this means that in some way we are trying to provide internal energy, or in some way we are converting internal energy to kinetic energy of the jet. Other means other possible solutions. When medium is on board, these are what we refer to as rockets. Then we have this other media that in reality are something different from the usual concept that we have of rockets, for instance, and here we have solar sails, tether, laser propulsion, or, as I mentioned, tether. So here we use other media, but you see, of course, this, except not on the top, all the others can be used in space. Laser propulsion, yes. So notice that this kind of devices are also can be considered as propellantless propulsion. So I just want to mention here that if we go to the air breathing engines that works in the atmosphere, of course you know that we have turbojets, ramjets, turbofans, and also pulse jets, different possible theoretical options. Of course we have, and probably you better know, the turbojet and turbofan that allow us to fly at not so high velocities for the common atmospheric flight. But if we are imagining to exploit, let's say, propulsion device for the flight in the atmosphere for a launcher, probably we have to keep in mind also the solution of ramjets or scramjets. Ramjets have, let's say, moved to a range of Mach numbers higher than turbojets. They allow to fly to exploit propulsion, atmospheric propulsion at Mach number between, let's say, more than 3 up to 5, more or less, and for even higher Mach number, to get propulsion, you have to burn the fuel at supersonic speed. It's just recalling you something, if you know. And this, of course, is a possible solution to fly at very high speed in the high atmosphere, and can be also part of a combined cycle engine for a more convenient reaching of the high altitude. So this is just to summarize, but here I would like now to pass.
Professore? Professore? Si sente un fortissimo brusio. E ora non la sento neanche più.
Non so se si sente ancora.
Aspetta. Sì, professore, si sente ancora.
C'è sempre uno. So it's just is everybody just one person told me that there is noise. Is true for everybody.
No, vero professore, c'è un rumore di fondo, comunque si sente molto piano la voce e si sente molto quel rumore continuo.
Così la voce.
E si sente sempre il rumore di fondo, magari possiamo provare a staccare il microfono esterno perché forse è quello che lo genera.
Così va meglio?
Perfetto.
Così va bene, mi sentite bene?
Sì, adesso si sente un po' meglio.
Un po'. Io pensavo bene. Ok. You have to think so many things. Okay, let's pass now to the classification of rockets. And so you see here that I left something open. That is the part relevant to rockets. And to do that, we have to first define what will be on the basis of our classification. And for rockets, what we do is to identify some principle on the basis of which to make this classification. And these are the way we get trust, what is the process that allows us to get trust, and
Professore,
sì.
è lo stesso problema di prima, solamente che è peggiorato, credo.
Sì, ma perché non me l'avete detto quando c'era qualcuno che mi dava una mano?
Si è risentito solamente adesso, è riaumentato di nuovo.
Mi sentite?
Provi a parlare un pochino.
Come?
Si può provare a parlare.
Sì, adesso sto parlando, prova.
Adesso si sente.
Senza rumore di fondo?
Sì, sembra che non ci sia rumore di fondo.
Adesso rivedete anche la lavagna?
Sì.
Benissimo. Adesso però mi devo ricordare dove stavo. So we were talking about the classification of rockets, and the most important thing that we use to identify, to classify rockets are the way we get thrust, what is the physical process we use to get thrust, and what is the kind of energy we exploit to get this thrust. Moreover, we have to take into account that we have a medium that you have to bring with us. And of course, we can use as a further classification the kind of medium that we have to bring with us. This is what we call the propellant or working fluid. So the first classification, now of course I will go in detail, but the first classification is about the process we use to accelerate our medium. And in this sense, we have thermal rockets, electric rockets, and nuclear rockets. So for the first family, that of thermal rockets, we can say thermal or thermodynamic rockets. And also for the second one, we can refer to electric or electrodynamic rockets. Before passing to describe in more detail the possible options that we have, I would like also to say that we will classify on the basis of the energy we use, but not only it's important the energy we use, but also where we take this energy, and this can only come from primary energy sources. So primary energy sources are typically only three, and they are primary energy they are the chemical energy, the nuclear energy, and finally the solar energy. So these are primary energy sources. The most commonly used is the chemical one, is the energy released by chemical reactions. So it's some energy that is within the chemical bonds and that can be released. So it can be considered as a primary energy source and can be available on board, but of course in a limited quantity. And the same is true also for nuclear energy. This time there are the nuclear bonds, so nuclear reaction as fission, fusion, or heat released by different kinds of nuclear reactions. And this, of course, can also is limited in principle because we have a given amount of nuclear fuel, and then we cannot extract more than what is available in this material. Of course, a different kind of energy is the solar one that is not available on board, comes from outside, and so is unlimited. I mentioned before also other kind of energy. For instance, the most cited one is, of course, the electrical energy, but you must consider this is a secondary energy. I mean, secondary because it's an energy carrier. We have to have a primary energy on board to generate electricity that cannot be stored as such. If we have a battery, it means that we have chemical storage of energy that can be released in terms of electricity. And or we have solar panels that allow us to get electricity, or we have nuclear power sources that allow us to get electric energy. Yes. Yes, you don't store electric energy. Electric energy is a carrier of energy. It's like what you store, for instance, in a battery, is the energy. It's stored in chemical bonds, and then it is released by chemical arrangement of these bonds. And this way, we have again release of electric energy. So it's a carrier that then can be exploited, of course, in different ways. But you have not it available on board unless you have some power generation to so let's start with the thermal rockets, and then I will stop at I don't remember the schedule, so I should stop at 1 and then start again at 1:10. So let's look to our thermal rocket or thermodynamic rockets. So it means here that we are going to exploit the conversion of internal energy of a fluid in kinetic energy. So I'm spending some time on it. So this is the reason is because I think it must be fixed clearly. So we are converting internal energy in kinetic energy, and we can do it in different ways. We can also do nothing, because if we have a gas on board, this gas has its own internal energy. It has a temperature. If we have a gas at room temperature, there is an energy inside, and we can exploit this energy also to have a gas at high speed, more or less high speed, and of course a thrust. This is what we call a cold gas rocket. What we exploit is the internal energy of the gas itself. So if I make here a table, we can identify the energy used for acceleration, and I put here nothing, known, better. Primary energy here. And then we have propellant. And finally, we have a number. So in this case, we have that actually we can consider further kind of primary energy, which is the internal one, what we have available. So here actually we have internal energy. In this case, we need to exploit the thermogas dynamic conversion of internal energy in kinetic energy. It needs that we have here a gas. And so we have a single propellant. And these are our cold gas thrusters. Then we have chemical reactions. So we have in this case as the primary energy chemical. Of course, here the primary energy has the goal to generate enough internal energy to be exploited in the conversion from internal energy to kinetic energy. So here the process, we are talking about thermal rockets. So I'm talking about how to, the different ways, means how to provide internal energy to our working fluid. So we provide this internal energy through chemical reactions, exploiting the chemical primary energy, and this can be done with propellants in a different status. So we can have here the status can be a gas, liquid, solid. Or we can also mix things. We can have liquids and solids, so we call hybrids. And here we can have 1, 2, even more propellants in principle. And this, so we have thermal rockets with chemical energy, so they are thermal rockets, chemical, and solid propellant, liquid propellant based. Then we can, to get our internal energy, we can also exploit electricity because there is a way of heating a gas through, for instance, resistances, or through electric arcs, or even microwaves. So you have different kinds of, we can exploit electricity here. The primary energy, in this case, if we use electricity, can be chemical, nuclear, solar. We can store our propellant in different phases. Typically, we have a single propellant, and we can consider, so for different kinds, we have resistor jets, arc jets, or microwave thrusters. Then we move I missed something here. Oh no. Okay. Here we can have also the as the mean of getting the internal energy. You can also use nuclear fission and fusion. Fission, yes. Fusion in principle. And get, of course, the primary energy will be nuclear in this case, but with nuclear fission or fusion, we get internal energy, and again, we can accelerate at high speed and get our thermal rocket. So here, typically, we consider liquid, but can be also gas. Or solid. Yes, can be also gas solid, but typically because you can, of course, gas is already at gas phase, but it will be difficult to cool a nuclear reactor by a gas. Solid, we can exploit your sodium with the heat of stored solid phase, and then you use the heat from the nuclear reactor to pass to a liquid phase. But here, okay, let's consider liquid and single propellant, and we have nuclear thermal rockets. These are called nuclear thermal rockets. And finally, we have also solar thermal rockets. There is not much room on the board, but I can write here that we directly use the solar energy to provide internal energy. We are heating our propellant. So the primary energy is solar. And here we have typically gas or liquids. And a single propellant. So in this table, we see most of propellants used in space propulsion, and it's almost everything, especially almost everything is here in the chemical propulsion. Of course, there are also applications for electrothermal propulsion, because this is electric and thermal. And also, this has been demonstrated. And this, of course, can be easily demonstrated. But most of the applications consider chemical propulsion. Now we stop 10 minutes, and we resume at 1:10. So can you hear me? Mi sentite remoto?
Sì, professore.
Sì.
Bene? Senza rumori?
Per ora sembra di sì.
So let's continue this classification, talking now about what we can call electric or electrodynamic rockets. And in this case, we have a different way of getting of accelerating our medium. And this is based on electrostatic or electromagnetic forces. So we have to consider a primary energy that can be chemical, nuclear, or solar. And then all of them can lead to electrostatic or electromagnetic acceleration of our medium. In this case, we need medium including charged particles to exert electrostatic and electromagnetic forces. So here we can identify different options that we can refer to as ion engines or colloidal engines or electrospray engines or thrusters and field emission electric propulsion. All these kind of devices are based on the fact that we apply an electric field on charged particles that are accelerated by this electric field. So for this reason, they are referred to as electrostatic thrusters. Electromagnetic thrusters exploit also forces due to the presence of magnetic field. And here we can identify all thrusters, pulsed plasma thrusters, magnetic plasma dynamic thrusters, or applied field magnetic plasma dynamic thrusters. And here, typically, we have a gas. Here we can have a liquid. Here we must have a liquid. And here we have a gas. Here we have a solid. And here, typically, we have a gas. So, in the Hall effect, thrusters, or stationary, also called stationary plasma thrusters, this kind of thruster can be seen both as electromagnetic or as electrostatic because it depends on how you see things, but I prefer to put this on electromagnetic group because at the end, the force acts on the magnets. And so it's there that we find our thrust. Because, as usual, also in this kind of propulsion, what happens is that you are accelerating through electrostatic forces your propellant, in this case, are charged particles. As a reaction, these charged particles exert a force or on your thruster. For instance, if you have, say, some solid part to which you exert your voltage that accelerates, that creates the electric field that accelerates the particle will exert a force on these solid parts as a reaction, and this will be your thrust. In case of all-effect thruster, what you have is that you will have a magnetic field through electromagnets or magnets, and what happens is that there will be a force that to accelerate your particles, you have to exert this force for these particles, and by reaction, you have that the electrostatic force is balanced, but you have some unbalance on the electromagnetic force that will result as your thrust. So, besides the need and the cost of creating charged particles, these kind of devices are also characterized by low thrust level, low level of thrust to weight. They are not able to lift themselves. So it's very low. They are characterized by very low thrust, and this is related to the fact that you have single charged particles that has to be accelerated. But they can be very efficient, and we will mention this shortly. But we have first to record what is the efficiency. So, without making further tables, I would like to mention the other options. When we talk about nuclear rockets, and we are not thinking of the nuclear thermal rockets that we mentioned before. The first family is those of when we use the nuclear energy to provide internal energy, heating a propellant. This second family is just to exploit directly the energy of nuclear reaction. That means, for instance, that you, in a new nuclear reaction, you have that your fission fragments, for instance, have a high kinetic energy. And if you are able to control this kinetic energy, you exploit this kinetic energy as the accelerated particle that you like to exploit. So this will require typically electromagnetic fields to control these fission fragments. It has been, of course, this is something that has been imagined but not used. And also another possibility is that of using controlled nuclear explosion. About the last family is that of propellantless propulsion means, like solar sails, or laser beams, or tethers. They exploit something which is not on board, so they are very efficient, but of course depends strongly on the environment you are considering. So independently of the way we are considering to get thrust, when we are thinking to create a thrust in vacuum, you will exploit in some way this, what is called the action propulsion often, or rocket propulsion. And one of the fathers of the rocketry, you know, the most famous people are Konstantin Tsiolkovsky, Hermann Oberth, and Robert Goddard. One of them, Goddard, in an interview on the newspapers, tried to explain why a rocket would work in the vacuum. He was ridiculed by this newspaper because says, how can you exploit this jet if this jet doesn't hit anything? Okay, so this can be, well, this rocket works because it pushes on the ground and go up. Of course, this is not the case, and you know very well. But of course, we have to know this. We have not to be wrong on this. So it's better to say, to repeat and repeat up to the moment I'm sure that all of you keep this concept clear. So in this kind of proportion, you have learned something like this, that you have in this reaction proportion, you exhaust gases. So you have you know this problem, I'm sure. You know this? We have the rocket flying time t1, the velocity v1, this direction, with a given mass. At a second moment, we have exhausted something with that time with a velocity, which is ue with respect to the rocket. And of course, this mass has been subtracted by the overall mass of the rocket. As a result, we have a velocity which is now equal to v2 v1 plus delta v. So if we consider that no other forces are acting on this system, well, of course, as usual, we make some ideal assumption. What happens is that if this, in this T1 and T2, we are considering no external forces, the overall momentum has not to change. And so we can say that the momentum we have at instant 1 will be the same as momentum at instant 2. And so we have this equality m1 v1. Let's say this is, you can call it m minus, this is the initial momentum, and in the second time we have to consider momentum of the rocket and of the exhausted mass. So the rocket will be, I don't know why I'm using this one, it's not me. It's v plus dv. This will be the momentum of the rocket, and we have now to consider also the momentum of this exhausted mass that will be, of course, its original, this is the velocity ue is with respect to the rocket, and so if we consider the absolute momentum of this mass, it will be v1 minus ue, which is in the opposite direction. So making a single one-dimensional problem, and I have to consider here plus delta m v minus ue. Okay, so we can simplify. We have mv equal to mv minus v dm plus m dv minus dv dm plus the delta mass minus UE delta. And so you can see that this cancels with this. And also that we have this term and this other, which are equal. And we can also see that if we consider small masses, it will be just a second order term. So with this, we have that m delta v is equal to ue delta m. And this works for sure if you are eating stones. It works perfectly. You have this delta mass, and you get, we say usually as a reaction, this delta V. And if you go to consider, if you are considering a fluid, instead you are usually, you go to the limit to small amount of masses which are exhausted, you refer to the unit time, and you imagine that you're doing things, you're exhausting mass continuously. So with these assumptions, we have that this will be m dv dt, and on the right-hand side, you have ue d m exhausted dt. So we can consider this, we can name this as dot m, and we get this expression, m dv dt is equal to dot mu e. This provides the instantaneous acceleration of our rockets and refers this quantity to the exhausted mass per unit time and velocity. And then we can call it this mass by acceleration. We are applying a force which results as a mass by acceleration. And this is our thrust. So let's make a comment here. I use this letter for indicating thrust and not T. Why? Thrust, I should use T. Most of rocket propulsion books use F for indicating thrust. Even if they are written in English, they use the letter F. Some strange, let's say, book use even if use the symbol T, perhaps use the thrust coefficient CF. This is rather strange, but okay, there's also someone doing this to state. But this comes from the fact that everybody is using F. Why? Because we are doing propulsion, and here 99% of propulsion is made in this framework with thermal rocket. And in thermal rocket, temperature is everywhere. So if you use T for temperature, you will never use two important quantities with the same symbol. Else you will be lost, or you will easily make errors. So this is why thrust in the propulsion word is called F and not T. Of course, there is some other. If you don't care about how thrust is generated, probably you can use T because you have no temperature problems anywhere along your trajectory, for instance. But I will use F there are some proportional books using T, of course, but I think it's the best thing we can do. And we will refer so to trust coefficient CF and so on. So just when we see here the stones that we eject from our vehicle to get thrust, we have to go back to what is thrust. It's a force acting on a vehicle. It's not a change of momentum. Change of momentum is the result of thrust. It's the change of momentum of the jet and of the vehicle. So I also like to quote a sentence here that I found interesting to expose this concept. In the absence of all contact with an external solid, I'm not driving the car, a prime mover can propel itself by ejecting a fluid or a solid mass toward the rear. I eject something this way, and I move on. I have a force in this direction. By convention, we say that this mover is propelled by jet propulsion, or through the propulsive force, our thrust, is the result from the effects of pressure and friction exerted on the wall of the hollow interior of the mover by the solids or fluids moving in the interior towards the exhaust nozzle. So, again, I am underlining once more this. What happens is that I am exerting a force through pressure and friction on the fluid. Fluid is accelerated. By reaction, this fluid is exerting a force in the interior of your body. Let's see this in a different way. Let's consider a box. Like this, and we have pressure inside acting on the walls. Only pressure because everything is stationary, we have no motion, we have no friction. This can be in the vacuum or in the atmosphere. What we see is that the resulting forces here is zero. Because the forces acting on these walls, of course, there will be, we should make the integral of pressure force along the walls, and should be this force equal to the integral along the surface of the pressure we have inside minus the pressure we have outside by the local normal, the local unit vector, and normal unit vector, and the elementary surface. So we see here it's very straightforward. We have, let's say, P minus PA by let's call it this way, the cross-sectional area, for instance, if this is Z, in this direction, there will be the area perpendicular to this. There will be this force over this surface, but we have the opposite surface here, and so we have also minus P minus PA, same area, and this would be plus another normal, but of course we can say this in this way, this is the direction and in general. So here we have that the force will be oriented the opposite direction. So these two terms cancels. This is true also if we consider this words, and also this one and the other one in the other direction. In general, what we know is that this is a constant that we bring it outside if pressure is equal everywhere as it is in a static condition, and we know that this is 0. If we consider, for instance, the normal, this is always the external normal to Earth's surface. So nothing happens. Now we consider another device. This time we have the possibility to fill this box with a gas at given pressure, but we can also consider this made of 2 parts. Actually, they are, let's say we have something that keeps the 2 parts close with each other with no leakage, and that can be at a given instant. We can open this, let's say, we can have a spring that keeps everything together, and then we can remove it suddenly. And we have pressure inside. So what happens at the moment? I give this command from remotely. I just say open this light. So what happens is that suddenly, you can easily imagine, these 2 parts are going to move in the opposite direction. And why? So we have that, for instance, the left half is moving here. And this is because at this point, if you go to the former integral, you see that we have no longer balancing forces. So consider the initial instant when I remove and I break this in 2 parts. We have a force which is exactly, this is the area, this cross-section area. So we have this F, and this could be internal pressure minus external pressure. Of course, the same is true also for the other part. Altogether, the momentum has remained unchanged because we have no forces coming from outside. So, but we can see that if we place this, for instance, this is blocked by a wall, this will move in this way, and I realize something that is moving. And this force will be rapidly decreasing because as this part is open, what is happening here is that we have some gas don't play. Okay, we have a gas here which is being exhausted, and rapidly pressure inside will decrease and will reach the external pressure because the gas is moving from the higher pressure region to the lower pressure, and is being exhausted by this device. So the problem is that I have that this box empties quickly, and we have that our force goes to 0, unless we try to empty our box at a slower pace. So for instance, if I take my box, and instead of cutting it in two parts, I just leave a hole, and I have some closure of this hole at the beginning, at a given time open, and at this point, we generate thrust exhausting the gas from this hole. Of course, in this case, we need more time to empty our box, so we have that our thrust will continue for a longer time, perhaps less, but it will continue for a long time. And so this is something that you know is exactly what happens to a balloon when you open the hole. You have this balloon is moving because of this thrust. So what we have to do, we have to keep this pressure inside constant. If we are able to do this, we will have continuous and controlled thrust possibly. So we have to provide, to keep the pressure, we have to provide here in some way, we have to refill our box. So we have a tank through which we refill this, and we have obtained a continuous proportion that can be also considered steady state. So if we see all of this, we are, it seems like we are considering something completely different of what we have seen before with V m delta V equal to UE delta M. Was in one case we focused on the velocity of the exhausted mass. Here we are just focusing on pressures. We have thrust because we have a different pressure here from here. We have thrust here because we have constant pressure everywhere. This is balanced, this is balanced, this is balanced from here. But here it's unbalanced. So we have that if this is the exhaust area, what we have here is an unbalanced force, which is P minus by the area corresponding to the unbalanced force. So here we see pressure, the other side we see momentum. Let's put it together. Let's put things together with what can be considered as an example of a rocket on a test bench on the ground. So we can consider this. In principle, it can move only in this direction, but we apply a balance here such that we have, we keep this in a fixed position. So this is what can be done in a test bench. This can be the measure of the thrust generated by our rocket. So we have that if we have a force generated in this direction, we can measure it by a spring, for instance, or in general by a balance. And what we can do here to analyze what happens is to consider a special control volume of shape and size constant, they not change. And we can consider the boundary of this control volume is our control surface. So our rocket can only move in the y direction, this one. And we are in an environment where pressure is the atmospheric pressure. So we have PA here, PA, and PA. And the environment is at rest. Nothing is moving, except that we have a jet, but it's outside of our control volume. So we are considering our rocket operating in steady-state condition, and this is still doesn't move because we have this counteracting force, which is in this direction, of course, and will be this F. Is equal to our thrust. The one that we measure on the balance and is the reaction force, it should be equal to our thrust. So for a fluid within this control volume, we see that the overall incoming and outgoing mass must be balanced, and so we see that the change of mass within the control volume in time is equal to incoming minus outgoing mass flow rate, and we see what we can also consider the balance of forces and momentum. So if we consider the sum of all applied external forces, this will lead to a change. Let's say here U M. This is for the whole control volume. Consider the masses inside and the velocity of each particle within this volume, plus of course the flux of momentum that we have on the boundary. So this is the control surface, and we have here you have to consider the elementary flow of mass at each point of control surface that will be given by density, velocity, and elementary surface in the direction with the velocity in the direction normal to the surface. By the velocity, we have the momentum. So here we can write so U by U and yes. So if we focus on this equation, we can see that there are external forces. Yes, we have one force, which is this one, is applied to our control volume, including the air surrounding the rocket and the rocket itself. We are applying the force to this balance. And then we are applying forces in y direction, also here and here, where we have this pressure acting in the direction I. So if I have to consider this term here, I would write that the sum this will be this F, which is in y direction, and then we have, for sure, if we call this as A left, then we call this area here A1, A2, and AE. Okay, so we can say, first of all, that we have at left a force which is PA, A left, and I, and on the right hand side, on this surface, I will have on this direction the force exerted by the pressure on our control volume. So the force exerted by the pressure is in this direction, and it will be so minus PA A1 plus A2 I, and then I left this AE because here we don't know which pressure we have. In general, we can have a different pressure because it's open. And so we also have PA, AE, and I. Then I should add also the force on top and possibly on the bottom, but I will not consider this because they are not in the Y, in the I direction, plus other direction. This includes everything relevant to the thrust direction. So we can also see here that if you are assuming steady state operation of our rocket, which is exhausting continuously its jet, getting a pressure PE effective and a velocity UE of this jet, so we have PE and UE there. If it's operating at steady state, nothing is changing its side. So the velocities, if we have some velocities, because there is a fluid inside here, so if you look to this integral, there will be that UDM is not zero, but the change of UDM, of the integral of UDM in time is zero if you are considering steady state operation. So this term vanishes. This sum of external force must be balanced by this quantity where we have a velocity. And we have that at these boundaries, the dashed boundaries, velocity is zero because we said that we are in an environment at rest. So this integral will be different from zero only along the region where there is the jet. So at the end, we have that this sum of external forces is F plus we have that if I consider A left minus A1 minus A2, we have AE. E must be equal to this one. If we assume constant velocity at the exit cross section, it will be rho E UE squared AE. Or if you recall that the mass flow rate can be identified as rho E UE AE, And so this is a different way to get the same result, but in this case for a fluid characterized by given pressure. And what we see here, that we have a new expression that is F equal to mass flow rate by velocity plus a pressure term, which is the difference of pressure multiplied by the exit area. So we have quickly seen this by this balance of forces and momentum. We identify in this pressure expression that is coming in this case from the balance between forces and momentum. So try to reconcile the two approaches that we have seen for the generation of thrust. And we identify that if we have this jet made by a fluid, which is accelerated, we have two terms, which is the first one, the impulsive thrust here, and the second one, which is the pressure thrust. With a special case when P is equal to PA, we call adapted jet. But we will go back on this. An important thing that I would like to underline at the end of this class is that if you look to this expression, you see that there is no mention of flight velocity. It doesn't appear. There is no dependence of the thrust we have generated our rocket by the flight velocity. If we consider, but of course you say, this is a test bench with zero velocity. Of course, velocity is zero, so it doesn't appear because it's zero. But if we imagine this done with in a wind tunnel where we have a velocity here and here, of course, in the momentum balance, because we have to consider also the continuity equation, you will easily see that these terms cancels. And so the result will be that there is no dependence on flight velocity of the thrust generated by a rocket, which is different from what happens in air-breathing engines. So this concludes today's class, and tomorrow will be in the afternoon class. I stop recording.